Hello everyone, this will be our last lecture in solid mechanics for this semester. In this lecture we have also two chapters about failure. So like we said in the previous lecture, we worked about yield criteria. It was about failure. Today we'll talk about two different types of failure, fracture and fatigue. So these two chapters are not directly connected. Both of them are about failure, but there are two separate chapters. So the first one will be about fracture. We study how we study fracture in solids, and second one will be about fatigue. So let's start with the first one. So what we talk when we say about fracture, what we'll study today exactly will be about linear elastic fracture. So about linear elastic materials, linear elastic fracture mechanics. So just as a reminder from previous lectures, as we said in the lecture about the types of materials, the material properties, the behavior of materials, we said we have two types of materials, ductile materials and the brittle materials. And we said that depending on when we do the stress-strain curve, depending on the curve that we have, we can separate between ductile and brittle. So as you can see, the ductile material is the material that we studied. The material that we have at the beginning, we have elastic zone, elastic region here. Then after when we overcome the yield strength, here we still have some what we call a yielding. This zone is of plastic deformation here. If when we remove the load, we will have a plastic deformation. And we'll have here the maximum point that we call the ultimate tensile strength. So the tensile strength here corresponds to the maximum point on the curve. And after that, at the end, we will have fracture. So that's what we call a ductile material. As you can see, it can undergo a lot of plastic deformation before fracturing. On the other side, on the other hand, we have what we call brittle materials. Brittle materials, as you can see, when we increase the stress and then as point directly without any yield, without any plastic deformation, directly it will fracture. So this is what we call ductile versus brittle materials. So the brittle material will fracture directly, while the ductile material will undergo some plastic deformation zone. So that's what's written here. But the idea is that in practice, in practical applications, we can see that some ductile materials also, they don't yield directly at some point here, they may fracture. So that's what we need to understand, what we need to study in this lecture. And under which conditions we can have fracture even in ductile materials without having some yielding. They can fracture at any point. So that's what we're studying here. We'll be studying. So what we need to understand that when we design a mechanical component during the manufacturing process, when we do the manufacturing, so the design on the computer, okay, is fine, everything is perfect. But when we do the manufacturing process, some flaws or some what we call defects or cracks may appear in the mechanical components that we design, that we manufacture. So in the manufacturing, due to the manufacturing process, we can have some crack or some small defects, some small flaws. So that's normal. That's not a big deal, always a big deal. Now in fracture mechanics, we analyze these cracks, we analyze these flaws to check if these flaws or these cracks are safe or not. So if I have, for example, this small crack here, let's say, we need to understand now. Our study will be about the cracks. How the crack is the crack safe or not? How can the crack be safe or not? It depends if it can propagate and grow, because if the crack can propagate and grow, it will fracture. So it will cause a fracture, what we call a failure of the structure. So the structure will fail. We'll have a fracture. So the idea in this chapter, we'll assume that we have a crack already in the material that we are studying, in the solid object that we are studying, and we need to understand or need to analyze this crack. Will this crack grow and cause a fracture or not? That will be the objective. So our aim, what we aim to answer in this lecture here, how we can predict if the crack would propagate and cause failure. What we need to do in order to predict if the crack will cause fracture or not, and at the same time, what is the permissible crack size? What do you mean by permissible crack size for a safe service? It means the crack size above which the component will not be safe anymore. For example, we can say if the crack is less than 2 millimeters, the component is safe. It's more than 2 millimeters, it's not safe. But based on what we can define these 2 millimeters, depending on what, that's what we will study. So to understand that, if I have a crack, we need to find the stress distribution around the crack. So that's the first part that we need to do, to find how the stress is distributed around the crack. And here, as we will see in this lecture, we define what we call a stress intensity factor. So that's what we'll study. This will be the main parameter that we'll study in this lecture. So the stress intensity factor. But before doing that, so here we need to define what's the difference between a hole and a crack. So as you can see, this is a crack and this is a hole. Now a hole, the example is this one is elliptic hole, and sometimes we have a circular hole. As a hole, the difference between a hole and a crack, that the hole is a part of the design. So I make the design for some considerations. I can make a design with a hole inside. So the hole is not a problem. I can make a circular hole, for example, if I want to reduce the size, the quantity of materials that I am using, I can make a hole inside here. So the hole is a part of the design, while the crack will grow, as we said, maybe it will grow due to the manufacturing process. So this one may be dangerous, maybe it's not safe. So this one is not part of my design. Now, before we study the crack, we need to understand that how do we model the crack? What is the difference between this curve, with this shape here and this shape? As you can see, this shape can be modeled as an elliptic hole with b when b tends to 0. So if b is very small, we'll have a very thin elliptic hole. So the crack can be modeled as a thin elliptic hole. So when the b over a, when b is very small compared to a, so the elliptic hole will become a crack. Okay. So the idea here, so before I study the crack, I need to understand how I can model the stress around a hole. Because the crack, we can say, is a particular case of a hole when the b is very small compared to a. So here, to calculate the stress presence of the hole, we need to define another parameter. So in addition to what we said, the stress intensity factor, here we define the stress concentration factor. So what's the stress concentration factor? That's the first part that we will study. So now let's take this plate. We have a plate, we have a tension here, F and F, a tensile test, simple tensile test on this plate, and we have another plate that we designed with a circular hole inside. Okay, so on this part we forget about the crack for a while. Just let's study a plate containing a hole. Now let's forget about the crack for a while. So what's the difference between these two shapes? This shape has a hole, a circular hole in the middle. So now how do we find the stress here? We know the stress, find the normal stress. Here we have a force is normal to the area. So anywhere I make a cut here, I can say that F over A will give me the stress everywhere. So it's very simple. Here I can say that the stress here is F over A, the stress here is F over A, but if I make a cut here to check what's happening inside, I cannot say the force over the area. I cannot say that the stress is equal to F over A because the area here is not the same as the area here, because here I have this hole. So it will change the area everywhere where I make the cut. So when I say sigma F equal F over A is not valid here everywhere, while it's valid here. So the presence of the hole will create some disturbance of the stress, because the stress is not constant everywhere. So here what we call where comes the definition of the stress concentration factor. So when we say stress concentration factor, why do we have here stress concentration? So for example here we have this what we call a hole, like the ones that we just studied. Here what we call a notch when the hole is on the sides. And this is a fillet when we have a change of area, a change of size. We have a fillet here. So both of the three, what's the common between these three different types of geometries? What's common between them is that in the three of them we have what we call a discontinuity. What do you mean by discontinuity? That here I have material, here I don't have material, then here I have material. Here is the same, here I don't have material, here I have material, here I don't have material, then here I have material. And here also the same, I have material, here I don't have material. So always when we have a discontinuity, we'll have, as we said, a stress disturbance. It will disturb the stress, because the stress will not be constant everywhere. So we cannot say that sigma is equal to F over A. So the presence of a hole or notch or fillet will cause a stress disturbance. So also we need to find what do we mean by stress concentration. So to understand what stress concentration, so for now we know that the stress concentration will be defined in the case of the presence of discontinuities. So let's take this example that we can face everywhere or anywhere in our lives. What's the difference between this door and this door? As you can see here, this door, we have an arc here, while this door, we have a right angle here. Now, usually in real life, we always can see that in some places, we have always some cracks that grow always in the vicinity of the right angle here. While it's very rare to find the same around doors with an arc. So it's very rare to find cracks here. So where does this crack come from? Why do we have cracks always in this kind of doors in houses? So here's the difference between this door and this door, that here we have a sudden change of shape. Here we have a straight lines, and directly we have the sharp angle here, right? A sharp change of shape. While the difference here is that the change of shape is progressive. So as you can see, the shape will be varying progressively because we have an arc. So it's like the difference here. Here when we have a fillet and without a fillet, here we have 90 degrees. Here we have this quarter circle here, let's say, or this arc here that will reduce the sharpness of the change of shape. So here they have what we call a sudden change of shape. Here the change of shape is progressive. So if we imagine the stresses as lines like this, here we can see that the lines will be changed abruptly, while here the lines will be changed progressively. So here what's happening here at this point here, when we see that the lines are very close to each other, with this what we call here that the stress is concentrated. So we have the stress concentration around these right angles, as you can see here, while here the stress will be smoothly changed. So always when you have a change, so both scenarios here, we have always stress concentration, because always around any continuity will have a stress concentration. But the more the change of geometry is sharp, the more the stress concentration will be greater. So that's here. For example, here the weight of the wall is causing a stress around the door, and here we have a change of abrupt change or a sudden change of shape will cause a stress concentration here, will create this crack. While here, because the stress concentration is lower than the stress concentration here, maybe we have a less opportunity or less probability to have a crack in this case. So that's what we just said here. A sudden change of shape will disturb the stress field around it. So here the stress will be disturbed around the change of shape. So here we define the stress concentration factor. So the stress concentration factor, how is it defined? So the stress concentration, we know now what stress concentration is. The stress concentration because we have a stress disturbance around any discontinuity, which will change the stress around it and will cause a concentration of the stress around it. So the stress concentration factor is a parameter that we symbolize by KT or KTN in the case of a normal stress. So from now on, every time we have a big N, it means normal stress. Or if I don't have any big N, it's for any case, including also the normal stress or any other case, we use KT. So how is it defined? Because as we know, let's take this example here. As we said, the sigma is equal to F over A here, or F over A here. But sigma is not equal to F over A here. Sigma will be greater here because the area is always lower. So sigma, the stress will be higher here. So how do we define the stress concentration factor? The stress concentration factor very simply is the maximum stress that can exist around the hole divided by the nominal stress. What do you mean by nominal stress? Nominal stress is the stress here, or the stress that would have existed if I didn't have any hole or I didn't have any notch. So the stress that I would have, it would be F over A. That's the nominal stress. So it's the stress that would have existed if I didn't have any hole in the plate. While the sigma max here is the maximum stress that will exist in the plate when the plate will have a hole or a notch inside. So the ratio between the maximum stress that the plate can have over the nominal stress, the stress that the plate would have had if it didn't have any hole or any notch, is called the stress concentration factor. So the stress concentration factor depends on the geometry, on the type of the discontinuity, as you can see. So if I have if the hole here or the notch is bigger, the stress concentration will be different. So we have a lot of parameters, geometrical parameters that will affect, but we need to understand that the stress concentration factor is the maximum stress around the hole here divided by the nominal stress, which is the stress that we know, force over the area. Now, how do we calculate the stress concentration factor? So this just to understand that we have different type of methods. We have analytical methods, so we do calculation based on the based on the theory of elasticity, which means that the stress tensor and the strain tensor and the relation between them. Computational weather finite element techniques like using computer softwares like the ones that we'll be using in the practical work. And there are also some experimental methods that are used depending on the type, as we said, on the geometry to find. So all these methods are just used to find the stress concentration factor in the presence of a hole or a notch or a fillet. As we said, what we care for now is the stress around an elliptic hole. So if I have an elliptic hole in the design, if I made a design with an elliptic hole inside, how do we find the stress concentration factor? Now here we can have a direct formula, the KTN, as we said in the case of normal stress here, or KT, is equal to 1 plus 2A over B. A and B are the geometrical parameter of the ellipse that I have here. So 1 plus 2A over B, it will give me the stress concentration factor. What does this mean? That if I have a plate that contains an elliptic hole, I have A and B of the elliptic hole. If I want to find the maximum stress that I can find in the plate, I can calculate the stress here, which is force over A. Then I calculate KT 1 plus 2A over B, so I have A and I have B, and then multiplying KT by the normal stress here will give me the maximum stress that can be found around the elliptic hole. So this is the same slide here. A and B, just as we said, A and B are the two parameters for the elliptic hole. So according on the value or the ratio of A and B, I will have different values of KT, of the stress concentration factor. And that's what we said at the beginning, that the stress concentration factor depends on the geometry, on the size of the notch or of the hole. And that's what we can find here. So this in the case of elliptic hole like this will be, I have more concentration factor, more stress concentration compared to a vertical hole, for example. So that's about the stress concentration factor. So the stress concentration factor, as we said, is used in the case of an elliptic hole, and as we said, the hole or the notch or the fillet are geometrical parameters that I put in the design. So I make as a design, I intend to put inside the design a hole that can be elliptic, that can be circular or a notch, or I can put a fillet. So these are parameters that I can control. At the beginning, we said also that if I want to model a crack, now we go back to the crack because that's our objective. If I want to model a crack, we said that we take it as an elliptic hole, but the B is very small compared to A. So I just have as if I have only 2A. I don't have any B. It's very small. So when we say the formula is for a normal hole like this, we said that the stress concentration factor is equal to 1 plus 2A over B. Now, in the case of a crack like this, B is very small compared to A. What means B is very small? So B over A is almost equal to 0. So if I want to use this formula here, I will have that the stress concentration factor will go to infinity because B is very small compared to A. So I have very extremely high values of the stress concentration. So the stress concentration can no longer be used because it will not be realistic. I will have very extremely high values, very close to very high values, so it will not be realistic. So we say that KT goes to infinity. So how do I do in this? So what we understand from this, so everything that we learned now for the stress concentration, okay, it's fine for if I have a hole that I make in the design, a circular hole or an elliptic hole like this. But if it's not valid when the plate has a crack, so I need to find a new parameter that represents the stress around the crack. So everything we learned for now, what we call stress concentration factor, is valid only for holes and notches that are already in the design. And so I have in the design or the plate that I am studying here a crack like this where B is very small compared to A. I will not be able to use the stress concentration factor. Okay. So that's what we said. If I cannot use because KT will go to infinity, I need to define a new parameter. This new parameter is what we call a stress intensity factor. So before we define the stress concentration factor, when you have a stress concentration due to the discontinuity in the plate, in the case of a crack like this, longitudinal crack, we define what we call a stress intensity factor. What's the objective of the stress intensity factor? We said the stress intensity factor, our objective is to find the stress distribution around the crack. So this is the crack, this is the crack here. I made it, I copied it here. As we said, we have 2a, the length of the crack. I have the applied stress here, sigma A, or sigma n if I have a normal stress. If I define any point here around close to the crack, let's say this point, this is the same point, just I made a zoom here. This is the crack and this is the point. I can make an origin here. This any point can be defined by the angle here theta and the distance r from the end of the crack. So I define any point. So the objective, so the stress intensity factor will help me to find the stress at any point having coordinates r theta with respect to this point here. So if I take any point, I will be able to find the stress using the stress intensity factor. So the stress intensity factor is only used for the case of a crack. So let's see how we. So that's the stress intensity factor. So we said this is the crack. We made zoom in. I want to find the stress around any point close to the crack. How it's defined the stress intensity factor? The stress intensity factor is defined as sigma a square root of pi a. What's square root of pi a and what's sigma a? Sigma a is the stress, the nominal stress applied here, is applied stress. When we say small a here, sigma a means the applied stress, while a here represents the size of the crack. So these two are not connected. The a here represents applied stress. So the applied stress multiplied by square root of pi a. But pay attention, what's written here? An infinite plate with a crack of length 2a in the middle. What's the mean infinite plate? It means that the length here is very large compared to the size of the crack. So the width of the plate is very large compared to the crack size. What do we mean by crack? What do we mean by very large? Which means it should be almost 50 times greater. When the length here is 50 times greater than the size of the crack, we can consider it as infinite plate. So in the case of infinite plate, we define the stress intensity factor as the applied stress multiplied by the square root of pi a, where a is what? Is the half, because 2a is the length of the crack. So a is the half of the length of the crack. So it's defined like this. While sigma a is the applied stress, externally applied stress. So we need to pay attention is that the stress intensity factor, it has a unit, megapascal square root of meter or Pascal square root of millimeter, or so it's a pressure or stress square root of length. So always Pascal or megapascal square root of meter. So that's how we define the stress intensity factor. Also, we said that the stress intensity factor will help us to find the stress at any point, the stress field at any point around the crack. So these are the formulas that are used in order to find the stress around the crack. So as you can see, K here is the stress intensity factor. Depending on the distance r from the crack and the angle theta with the crack, we can find sigma x, sigma y, and tau xy in the plate. Now these are the formulas. That we need to understand from this part here is that we can, using the stress intensity factor, that's the first objective, you can using the stress intensity factor to find the stress field around it. At any point we can find the stress field around the crack. That's the first. We don't need to memorize this. We just need to understand that it can be used to find the stress at any point around in the vicinity of the crack. So that's what we need to understand from this. What's the most important part is how we calculate the stress intensity factor for an infinite plate with a crack. If I have the size of the crack, we have the stress applied on the plate. I just use sigma square root of pi a. So here's an example here. Find the stress intensity factor applied to infinite plate with a crack of length 20 millimeters when the applied load is 100 megapascal perpendicular to the crack. So we have because the stress here is perpendicular, so normal, we call it big N. So sigma N here is 100 megapascal. This is the applied stress. The length of the crack is 2A is 20 millimeters. I need to find the stress intensity factor. So this problem is very simple, just a direct application. We know because it's infinite plate, K is equal to sigma N square root of pi A. The applied stress square root of pi A. The applied stress is 100 megapascal. Pi is pi, and A is 0.01 meter because 2A, the length is 2A. You need to pay attention. 2A is 20 millimeters. So A is 10 millimeters, so 0.01 meters. So 17.7 megapascal, because we kept the stress in megapascal, square root of meter, as we said. That's the unit of the stress intensity factor. Now the stress intensity factor in different geometries. So what if the plate is not an infinite plate? What is the width is not very large compared to the crack size? Here we need to multiply the sigma square root of pi a. We need to multiply it by what we call a geometry factor, y. So the geometry factor is used only if the plate size is not very large compared to the crack size. How do we calculate y? We have graphs. For example, in the case of a central crack, here we have a over w. So the a over the width. So if I have the crack size, I can divide a by the width. Let's say it's equal to 0.3. So I come to the graph here 0.3. I find, let's say, 1.50. So I need to multiply 1.50 by times sigma times square root of pi a in order to find the stress intensity factor in such a plate. Now let's say we have a different also another example of maybe the crack's not always in the center. So in the previous examples, the crack was always in the center. Now let's say in this slide, a crack is not in the center. It's what we call an edge crack. In the case of an edge crack, also we need to multiply the sigma square root of pi a by a geometry factor. And here also we have in a different graph. Also we use the graph. We divide a by w, and depending on the value we can find y. So y is only a geometrical factor used when the plate does not have an infinite width. For example, this is an example here. Find the applied stress intensity factor. We have the applied stress is 100 megapascal, A is 10 millimeters, and W is 5 centimeters. So A here is the size of the crack here on the edge crack, and we have the width is 5 centimeters. So here we apply the formula. Which formula we need to apply? Y sigma square root of pi a. We need to multiply here by y. Because we don't have an infinite plate. We have a plate with an edge crack. So how do you calculate y? We need to use this graph. So this graph, we need to find a over w. So the a over w is 0.1 centimeter over 5, so 0.2. So this is 1.5. Let's correct it. So 1 centimeter over 5 centimeters, 0.2. So we come here to the graph 0.2. We find the corresponding value of y 1.36. Then to find the stress intensity factor, K is equal to 1.36 y times sigma 100 times square root of pi 0 times a. So as direct application of the formula, we can find the stress intensity factor in the case of an edge crack. So depending on the size of the crack, we'll have a different A over W, we'll have a different Y, and we'll have a different stress intensity factor. So that's about the stress intensity factor. Now, in all the cases that we studied here, we just took the case of a normal stress and a crack either on the edge or in the middle. Now, just to remind, so as we said at the beginning of the lecture, the fracture mechanics is we need to understand how the crack will propagate or not. Now, in the beginning here, in the beginning of the last century, all the mechanical components were designed using only sigma y, the yield strength. So as we said in the previous lecture, so the only failure that was taken into account was only the yield criteria. So only we used to design everything based on the yield criteria. But we did not pay attention to the little cracks or little defects. We did not consider them in the design. But after that, we find that in some cases we have always even a small crack can cause the failure of a large mechanical system. So everything now we studied about the cracks and about the stress intensity factor, we need to understand how we use it in order to check if a crack will propagate and cause failure or not. So that's the objective of linear elastic fracture mechanics. Will the crack grow and propagate, and what are the conditions under which it will or it will not propagate? So before we continue, we need just to also to understand. For example, let's say I take this example here. I take this cut here. I have a crack, the same crack here and the crack here. Here we define what we call a mode of crack opening. What do you mean crack opening? The crack maybe it will propagate, so it will open. How it will open? If I have three possibilities here. Either I have a normal stress here that will try to open it in this direction, so this size here will increase. I can have also a shear stress I can have here, so I try to move it in this way, so also it will increase in size, but in this direction like this. And the third mode, if I have a stress in this direction, so I try to move this to the right and this one to the left, so it will open also transversely like this. So this is what we call three modes of crack opening. So in the first mode, as we can see, we have a normal stress in which if I take this XYZ, if I put this reference system here, we can see that here I have a normal stress causing it, sigma Y, which will be causing the opening of the crack. Here I will have a shear stress, as you can see, because it's in this plane. A shear stress in which plane here? As you can see, if I look, this is the plane parallel to, so on the XY plane, I have it on the face here, on the same plane of the crack. And the third one is, if I look at it, it's here, it will be in which plane? In the YZ plane. So two modes are based on shear stressing, and one is based on a normal stress in the Y direction. So I need to understand that we have different modes of opening. So the only one that we studied is normal, is the mode 1. So this will be we focus on this type. When the normal stress, in this case sigma YY or sigma Y, is opening the crack. Now, for the idea is that everything we said before, that the stress intensity factor is equal to sigma square root of pi a. So here sigma will be sigma Y. So that's the formula that we defined before. So the idea about these three modes, that every time when we say the applied stress, and for every mode the applied stress will be different. Okay, depending on, so for the mode 1, when we said that sigma will be equal to sigma y, in mode 2, the applied stress will be equal to 2xy, and here in the third mode the applied stress, so as we found here, so every time depending on the mode that I have, the applied stress will be different. So that's the only idea here, that when we say applied stress, it depends on the case that I have. So it's not always a normal stress, or it's not always in the same direction. So that's the idea here. Now the idea is that after I find the stress intensity factor, depending on the mode that I have, so after I find the stress intensity factor here, how do I know if the crack will propagate and cause failure or not? Here we'll have we will not go a lot into the details of the method. It's not on our program here, but we need to understand that we have two conditions depending on Griffith approach. So Griffith is a scientist who defined two conditions for the crack to grow. So the first one is that the bond at the crack tip, so the bond at the crack tip must be straight to the point of failure. So we'll see that. The most important one, the amount of strain energy released must be greater than or equal to that required for the surface energy of the two new crack faces. So the first one is that we have the stress at the crack edges should be very high, what we call the point of failure. The second one is that the stress energy that will be released if the crack will propagate should be greater than the what we mean here by the surface energy of the two new crack. What we mean here by what means these are the two stress. Are the two crack faces here. So every time the crack grow, the idea is that the strain energy released when the crack will grow should be greater or equal to that to create the two new faces, because I have two new faces. So every time I grow, I have two new faces. So we don't need to go into the details of this, because this will be a separate study, advanced study. So everything is written here just to understand the two conditions. But you need to understand that based on these two conditions, if we develop these two conditions, especially the second condition here about the strain energy, so everything related to the strain energy, we find that the stress intensity factor that we defined, sigma square root of pi a, should have a critical value. It has a critical value, what we call Kc, what we call a fracture toughness. So what's fracture toughness? Fracture toughness is the critical value of K. When the stress intensity factor is greater than Kc, the crack will propagate and cause failure. So that's the idea here. So that what we define from all of this, that there's a property, what we call the fracture toughness, is the critical value of K. So when we calculate the stress intensity factor, I will have Kc given, or I can calculate it depending on the problem. If I have Kc, I calculate the stress intensity factor. If the stress intensity factor that I calculate is greater than Kc, then the crack will propagate. If not, so the design is safe. So okay, as always, for each mode of opening, we have different Kc. So the Kc, as you can see, depends on the material. What do you mean depends on the material? It's a material property. So if I calculate Kc, let's say for steel, It will be always for steel, but it doesn't only depend on the material. On some other conditions, it depends on what? On the mode. For example, on this mode, if I open the crack in this way, I have different fracture toughness if I open it in this way, and also different if I open it in this way. So for each mode, I have different fracture toughness. But for each one, the fracture toughness is what? Is the maximum value that the stress intensity factor can have without causing the propagation of the crack, without having a fracture. So let's take this example to understand the concept. Applying linear elastic fracture mechanics finds the maximum stress that can be applied to an infinite plate with a crack of length of 10 millimeters. We have here the stress, we have here the Kc. When we say K1C or Kc, it's a fracture toughness. That's the one that the parameters that we just defined. So the fracture toughness here is given 60 megapascal square root of meter. What's this fracture toughness, as we said, is the maximum value of the stress intensity factor that we can have without allowing the crack to propagate. So what we need to do, for example, if I have any stress here is given, let's say I have 30 megapascal as a stress. How do I know if this stress will cause the crack to propagate or not? For the stress, I calculate the stress intensity factor, the one that we defined, sigma square root of pi a. Then if the stress intensity factor is greater than 60, then I will say that the design is not safe, the crack will propagate. If it's lower than 60, the design is not safe. It's lower than 60, the design is safe and the crack will not propagate. But here the question is, find the maximum stress that can be applied to infinite plate with a crack of length 10 millimeters. That's the question here. So that's how do we find this? We know that the stress intensity factor is sigma square root of pi a. So here we have infinite plate, so we don't need to multiply by y. So sigma square root of pi a. We can find that if I replace a here by 0.005, because 2a is equal to 10 millimeters, so a is equal to 5 millimeters. So we can find that the stress intensity factor is 0.125 sigma. So every time I put a stress here, the corresponding stress intensity factor will be equal to 0.125 sigma that I'm using. To prevent a fracture, the stress intensity factor should be lower than the fracture toughness. That's the condition. Now the stress here, the stress intensity factor always should be lower than the fracture toughness, because if it exceeds the fracture toughness, the crack will propagate. So this one should be less than 60. So the stress intensity factor should be less than 60. I can find that sigma n should be less than 480 megapascal. So the maximum stress that I can apply to a plate like this, it will be 480 megapascal. Why? Because if I put, let's say I put 600 megapascal as stress here, if I calculate the stress intensity factor 0.125 times 600, it will be greater than 60, and then it will not be safe. It should be less than 480 for this one to be less than 60. So for the stress intensity factor to be less than the fracture toughness in order to have a safe design. So this is so what we need to understand about the stress intensity factor is this. We calculate the stress intensity factor. If the stress intensity factor is less than the fracture toughness, which is a property of the material for the load that I have, the design is safe. If it's greater, the design is not safe. That's the summary of what is the main use of the stress intensity factor. Finally, here this is what we call the failure assessment diagram. Here, the failure assessment diagram is a diagram that is used to combine the two types of failure that we had in this lecture and the previous lecture. In the previous lecture, we studied the yield. When we said that the stress should be always lower than the yield strength in order to prevent for a simple tensile test in order to prevent plastic deformation, panel deformation. Then we studied the yield criteria, the von Mises and the Tresca criteria. Here, this is for a given load, for a simple load that's like the ones that we studied. We have what we call a failure assessment diagram. We can see here the applied stress intensity factor over the fracture toughness. So Kc, every time I have Kc is the fracture toughness. If I have only K or Kap applied, is the stress intensity factor. And we know that the stress intensity factor should be always lower than the fracture toughness in order to have a safe design. Also, the applied stress should be always lower than the yield strength, so the sigma y, in order to prevent yielding. And here this is what we call linear elastic fracture mechanics. Here was this part here what we call elastic plastic fracture mechanics. This is outside our program, so we did not study it. But the idea is that this diagram here is used. I need to at the same time ensure that the stress should be lower than sigma y, and that the KAP is lower than so the stress intensity factor is lower than the fracture toughness. So this zone here will be safe, and any point is outside this diagram will be unsafe. So when do we use this diagram? This diagram as it's written here is for very high values of stress when the linear elastic fracture mechanics is not always valid. So this diagram we will not be using it always. It's only used in particular cases when we are afraid that we will have a new type of failure that we did not study, the elastic plastic fracture. But just to understand how we use this diagram, I will let's see directly this example. A 5 mm crack was found in a component that is under a nominal stress of 200 megapascal. So 200 megapascal is what? It's the applied stress. The applied stress is given 200 megapascal. I have a 5 mm crack inside. The material properties are the yield strength is given 250 megapascal. So the yield strength is the stress above which we will have plastic deformation. And KIC, so the material properties, the KC is the fracture toughness is given 100 megapascal square root of meter. When you're using the failure assessment diagram, this diagram, we need to determine if the component is safe or not. How do we do this? We need to find sigma up, the applied stress over the yield strength, and we need to find the applied stress intensity factor over the fracture toughness. So what's the applied stress here? Is 200 over 250. We find 0.8. How do we find the stress intensity factor here? To find the stress intensity factor, like we did before, it's sigma square root of pi a. If we do the calculation, we find that the applied stress intensity factor is 17.72. So we divide the stress intensity factor 17.72 by 100. It's given. We find 0.17 and 0.8. So I come to this diagram here. I will find 0.8 and 0.17. So the point will be here, let's say. So this point, as we can see, it's inside the safe zone. If the point was here or was here or was here, the design will be safe, will be unsafe. So because the point here is in the safe zone, so the design is safe. Now, if the point was here, it will be unsafe, and at the same time, we'll have what we call a plastic collapse. So what's mean plastic collapse? Means that the failure will be due to plastic deformation. It will not be due to fracture or to fracture mechanics. If the point that we find finally is here, it means that the failure would be due to fracture. And the point that I found here, it's also fracture but elastic plastic. So the idea here is that I use this diagram in some cases only to combine the two failure mechanisms. Okay, so that's the idea about the stress intensity factor and about the fracture toughness that we need to understand. Just to remind at the end of this first chapter is that at the beginning, what's the difference between stress concentration factor and stress intensity factor. So the stress concentration factor, as we said, is if I have a design containing a hole or a notch, so it's a part of the design, it's not a problem. I want to find the maximum stress around it. We use what we call KT, is the maximum stress over the applied stress or the nominal stress. So that's what defined. Then we said that if I want to model the crack as an elliptic hole with very small b, the stress concentration factor is not enough. Cannot be used. So we define what we call the stress intensity factor. So every time I have a crack, I don't use the stress concentration factor. We use the stress intensity factor, which is calculated as sigma square root of pi a for an infinite plate. And as we said, how do we use this one? Every time I calculate this stress intensity factor, if it's lower than the fracture toughness, I have a safe design. If it's higher than the fracture toughness, the crack will propagate and the design will fail. So this was everything about the first chapter about the fracture mechanics, the linear elastic fracture mechanics. In the tutorial, we have a lot of problems about the stress intensity factor and about fracture toughness, and then we have some problems about the difference between the stress concentration factor and the stress intensity factor. So now we can go and continue with the second part of the lecture will be fatigue. So now we finish with the fracture. Now we have a new part. As I said at the beginning, it's also about a failure about failure in solid objects, but it's a different type of failure. So we need to now to consider a different part. So everything we learned before now is a different part about everything that we learned from now until the last slide. So what we need, just to begin with fatigue. What do we mean by fatigue? So let's take this example. If I have a wire like this, I want to cut it. I don't have a wire cutter. I just want to cut it using my hands. What can I do? I have two possibilities. The first one, I can put tension here. I put one hand here and one here and start pulling from two sides. Or easier, I can put my hands like this and start pulling up and down here and here, as you know. So here up and down, up and down. So I will bend it upwards and downwards repetitively, consecutively. Or I can do this. Both of them, maybe, finally, both of them will be able to cut the wire. But of course, this one will be faster, will be quicker. And here the most important, I will need a lot of force. Here I need less force than this case. So if I do the same stress alternatively, or the same force alternatively, with less force, I will be able to fracture here, to cause a fracture. So this is the idea of fatigue in general. That's what we'll study, but we'll study it briefly. So also some reminder. What did we say about the tensile strength? Like we said at the beginning of the lecture, that the tensile strength is the maximum stress that the material can withstand before fracturing or before breaking. So if every time I have the stress less than the maximum the tensile strength, the material is safe here. Okay, if I don't have any crack. So every time I have a stress lower than the tensile strength, the ultimate tensile strength, the material is safe. It will not have any fracture. But the idea is that if I have a repeated load, like we just saw in the previous example, if I have a repeated load, even if the stress of this load is less than tensile strength, if it's repeated, if I am doing repeatedly on the same point, I will have a crack that will grow and will cause a failure of the component. So also I don't need always, so I don't need, even if I have a stress less than the tensile strength, if I let's say I take this stress here and I start to repeat it on this specimen, repeat it. After all, it will break. Why? Because this load is repeated, even if the stress is less than the tensile strength. Now, what we need to understand that many, if not the most of the failures that we have in mechanical components are due to this mechanism. This is what we call fatigue. So fatigue is a failure that will occur when a repeated stress is applied to a mechanical component, even if the stress is lower than the tensile strength. So fatigue, for example, this example here, why do we have here always the contact between the wheel here and the rail? Always the contact, every time I have the full turn, I have a contact at the same point. So this is what we call a repeated stress. Or a more practical example is the gears. When I have torque here and torque here, always, after one full round, at the same point, I will have a repeated stress. So the repeated stress are very frequent in our daily life, and practical. We have a lot of practical examples about fatigue problems. Here, how do we do the fatigue testing? How we do it in the lab, in the experiment? What we can do, we can take very simply the tensile machine. We put a specimen or a coupon here. So as a specimen, we apply the force, the same one, but instead of only applying one time the force and try to increase it and have the stress strain curve, we define one point of the stress, let's say 50 megapascal. Or let's take this example here, I have 5, let's say I have a stress of 5 megapascal. And instead of applying one time the stress, I'll try to start to alternate, as you can see. So we change the stress. So we increase the force, then we decrease it. Then we increase it, then we increase it, decrease it with time like this. So we have what we call alternative stress or periodic here stress. So the specimen undergoes a cyclic stress. So cyclic stress or alternative stress. Alternating stress. So alternating stress or cyclic stress is stress varying periodically with time, and we continue this until we have failure. So as you can see here, every time we go back to the same point, we call it one cycle. For example, this is one cycle. So what we do, we define a stress and we start to change And then when it stops, when it will have failure, we count the number of cycles. How many cycles did it take in order before breaking? That's what we calculate. So this is the main parameter here. The number of cycles are very important parameters. So the first one will be the stress between alternating or varying or cyclic. And the second point that we need to calculate is the number of cycles required for failure. So these are the two parameters that will define the fatigue. So this we need to understand clearly what we mean by cycle. So as you can see, what's happening here, we are increasing from 5 to -5, then to 5 to -5. What means that I am doing a tension. I go back to 0 without any force, and I do a compression. Then tension, compression. As you can see, tension, compression. Compression means the stress is negative, that the force is trying to compress the specimen. So tension, compression, and 0 is the main value here. And then we check the number of cycles. This is one type of tests that are done. So that's it. This if I take this is a random or a default alternating stress. We have always a maximum value of the stress, a minimum value. So here defines the one cycle, as we said, is when we go back to the same point. So this is one cycle. So here we define what we call what's important parameters. It's the mean stress. What is the mean stress? It's the mean value here between the maximum and the minimum. So the maximum plus the minimum over 2. The stress amplitude. This is the stress amplitude. It's the difference between the maximum and the mean, which can be calculated as sigma max minus sigma mean over 2. So it's the difference between sigma max and the mean stress. So that's the amplitude. It can be this or this. So the amplitude. So it's similar to any cyclic or to any periodic curve. We have the amplitude, we have the mean value, we have the maximum and the minimum. Stress range delta sigma is the difference between the maximum and minimum. And also an important part, the stress ratio is sigma mean over sigma max. So the minimum sigma over sigma max. This is the stress ratio. Now here, as you can see, sigma mean the mean stress sigma m, the mean stress is not 0 in this case. It can be 0 if I have tension compression like the previous example. In this case, it's not 0. So here we defined also different conditions of loading. So what we call the fully reversed, when the R is equal to -1, when sigma minimum is equal to minus sigma max, that's what we call the tensions and compression. So the mean value of the stress will be equal to 0. We have a different load, what we call 0 to max. So we don't have any compression, just tensions and 0. Tensions and 0. So sigma m will be here the mean stress. Or 0 to mean only we have compression. So we have zeros and compression. Zeros and compression. So these are different loading conditions. We don't need also to have 0 everywhere. We can have, like the previous slide, we can have any two random values of the stress. And we'll see later how we can define the number of, how does this affect the number of cycles that we will have at the end. So an important curve the important analysis that we use is the SN curve. So what's the SN curve? We need to understand what's each term. So as you can see, we have XY reference here. On N here we have the number of cycles to failure, and S here is sigma A. So S is the alternating stress amplitude, N is the number of cycles, and F is the number of cycles to failure. So this NF here is the number of cycles to failure. So let's read. The SN curve is the simplest way to analyze the fatigue problem. What's the fatigue problem? We had a stress, as we said in the previous slide. We are alternating the stress. We have the stress amplitude, the maximum stress minus the mean value. And for each stress, as we said, we take the specimen for each stress amplitude and we calculate the number of cycles needed in order to have failure. So here, that says the cycles required to failure at a certain stress are plotted normally in a logarithmic graph. Some materials such as steel show a fatigue limit, sigma f, or endurance limit below which the fatigue life is essentially infinite. So let's understand this curve. What's the mean, for example, 600? If I take 600, I will have, let's say, 10 power 4. What does this mean? This means that if I take this specimen, like the previous example, I put a stress of 600 megapascal, and I do an alternating stress from 600 to -600, 600 to -600. I will need to wait 10 power 4 cycles, so 10,000 cycles, 10,000. I need to do this 10,000 times before I have the fracture. Now, if I put, let's say, 700 here, I will have less number of cycles. If I put, let's say, 500, let's say, I will have 10 power 5. What's mean for 500? I will have 10 power 5. Which means I take another specimen of the same material now, and I put an alternating stress with an amplitude of 500 megapascal. And now it will take 10 power 5 cycles to failure. So if I put an alternating stress, so if I go back here, if I put an alternating stress of 600 megapascal on the specimen, it will take 10 power 4 cycles to failure, so only 10,000. If I reduce the alternating stress, that's normal. I reduce it to 500 and do the alternating stress for another specimen, it will take 100,000, 10 power 5 cycles. So every time I increase the stress amplitude, it will take less cycles to failure. And of course, if I reduce the stress amplitude, because I'm reducing the stress, it will need more number of cycles in order to fail. Now, as you can see, what's the fatigue limit here? As you can see, if I take, let's say, for 450, I can say 450. I don't have any point on the curve. What does this mean? That if I take the specimen and I apply on the specimen. Let's say I take this specimen here and apply a stress, alternating stress of an amplitude of 450, it will never fail. That's the meaning. So any stress below this limit here, even if I do it 1 billion times, 10 billion times, it will never fracture. So that's the meaning of fatigue. The stress below which it will never fracture, even if I have an alternating stress. This is what we call the fatigue limit. So the fatigue limit is the stress below which I will never have any failure, even if I repeat the stress infinity times. So this is the sigma E here, the endurance limit, or the sigma F. So that we need to understand the SN curve, that for any stress amplitude I can find the corresponding number of cycles. That's the meaning of the SN curve. Now the SN curve, normally we don't use the SN curve as it is like this. For example, for the materials that we use, we will see that later, we have a linear approximation of the curve. Here another example of a stress fatigue testing machine. This one here, as instead of having an axial load like a specimen, as you can see, we have this system here. Every time this one turns here, it will make a stress here. So if I increase, of course, every cycle here, we note the cycle. So here, as you can see, I have sigma to 0 because I have stress, then 0. So as you can see, we can change the velocity depending on the speed. Here we'll have a different number of cycles. So this is also just an example of a different testing machine. Now going back to the SN curve. The SN curve. So this is just an example from real experimental data here. So as you can see, this is what we find in the experiment for different materials. And this is the line that we plot as approximation of that we use in our as a property of the material. So the SN curve here, we are always in the SN curve. Here we have the S, here we have the N. So this is the amplitude. When you say sigma here, I mean the amplitude of the alternating stress. And here's the number of cycles corresponding to each amplitude. So this approach here, the linear approach, is used for some metals, especially for steel. For steel, we use this linear approach. Instead of having the curve that we found before, we use this linear approach like this. And this all is mainly used between 10 power 3 and 10 power 6. So what the idea is that between these two values here, I don't need to use a curve. I can have a formula to give me the sigma n with function of n. Now let's see what's the meaning of sigma n and what's the meaning of n here. So what do you mean sigma n is equal to 10 power c n power b? N is the number of cycles. Sigma n is the amplitude of the applied alternating stress. So sigma 1000 equal to 0.9 sigma ts for steel. What do you mean sigma 1000? When we say sigma n, sigma 1000. So for steel, we know that sigma 1000 equals 0.9 sigma ts. Ts is the tensile strength, which means that if the alternating stress has an amplitude of 0.9 sigma ts, the specimen will break after 1000 cycles. So if the applied stress is equal to sigma ts, if it's equal to the tensile strength, the the specimen will fracture on sigma ts, because that definition of sigma ts is the maximum stress that can be applied. If 0.9 sigma ts, if I apply a stress of 0.9 sigma ts, if I apply the stress only one time, the specimen will not fracture because the stress here is lower than sigma ts. But if I apply it 1000 times, if I apply it 1000 times as alternating stress, this for steel, the specimen will break, it will fracture. So if I apply as even if the stress is lower than sigma ts, it will break after 1000 cycle. For example, if I want to find the sigma 10 power 4, what do you mean sigma 10 power 4? I want to find the stress that I need to apply alternatively in order to have a failure after 10,000 cycle or 10 power 4 cycle. So I put here n, I replace n by 10 power 4. Okay. So what are B and C here? What B and C are? B is defined as sigma 1000. What means sigma 1000? Is the stress that need to be applied 1000 times in order to have fracture, which is in the case of steel equal to 0.9 sigma ts. Sigma 10 power 6, what's sigma 10 power 6? Sigma 10 power 6 is the stress amplitude that I need to apply in order to have failure after 1 million cycle. So always, of course, sigma 10 power 6 will be lower than sigma 1000, because sigma 10 power 6 is the stress that I need to apply 1 million times alternatively before fracture, while sigma 1000 is the stress I need to apply only 1000 times in order to have a fracture. Also for steel, so for steel, now for materials, sigma 10 power 6 is a given property. Sigma 1000 is a given property for any material. But only for steel, we can say that sigma f as the fatigue limit, the one that we defined as the previous, the fatigue limit here, is equal to sigma 10 power 6. And sigma 1000 here, sigma 1000 here is the stress that the amplitude is equal to 0.9 sigma ts for only for steel. Here sigma 10 power 6, but just to remind you what sigma fs equal to sigma 10 power 6, that after 10 power 6, so the stress curve will find here, any stress below sigma 10 power 6 or sigma fs for steel, I will never have failure even if I repeat it 1 billion times. Okay, so that's the fatigue limit here. So also to summarize all this slide, this formula can be used if I have this amplitude of the stress, alternating stress. If I have the amplitude, I can find the number of cycles that it will take before fracture, or if I have the number of cycles, I can find the corresponding stress amplitude. C and B are formulas that they need to memorize these two formulas. How do you calculate B and C? I use sigma 1000 and sigma 10 power 6, which are properties or given properties of the material. Now this is an example here, knowing the fatigue limit of steel. So of steel we have sigma fs is 100 megapascal, the tensile strength is 250 megapascal. Find the maximum stress that can be applied if the piece should be in service for at least 250,000 cycles. So that's the question here. We have we need the stress that can be applied, the maximum, the stress, the amplitude of the alternating stress that can be applied if I want the piece to be in service for at least 250,000 cycles. So this is the formula that I use. I know that n is equal to 250,000 cycles. We need to find the corresponding sigma n. So sigma n is equal to 10 power c n power b. So b is given using this formula, c is given this formula. These three are the same formula. This is a formula that I need to use. I have n, I need to find sigma. How do I find, to find sigma if I have the number of cycles, I need to find C and B. So sigma 1000, as we said, sigma 1000 for steel is equal to what? To 0.9 sigma ts. So I multiply this by 0.9, it will give me sigma 1000. Sigma 10 power 6 is what? For steel is the same as sigma fs, so I just replace it by 100. And as we said, sigma 10 power 6 is always lower than sigma 1000, of course. So just also to remind, what do you mean sigma 10 power 6 is equal to 100? It means that if I apply the stress of 100 megapascal 1 million times, alternating stress of 100 megapascal 1 million times, the specimen will fracture. What does mean sigma 1000 equal to 225 megapascal? It means that if I apply a stress with an amplitude of 225 megapascal for 1000 times only, the specimen will fracture. And also to calculate C, I just use the same formula for C. And I find C and B and just replace C and B here with n 250,000. I can find the corresponding stress. So this is the stress that if I put a stress of 117 megapascal, I replace 250 here, 250,000, which means that if I put a stress of 117 megapascal, the specimen will take 250,000 cycles until fracture. That's it. Another example here. Okay, so this is the detail of the solution here, the detail of the solution that I just showed. So for steel, we have sigma 10 power 6 equal to sigma fs, sigma 1000 is 0.9 sigma ts. I can find B and C directly. I know that n is equal to 150,000. I can find the sigma n. So this is the same example that I just showed. So we need to understand that for everything that we learned here, sigma n equal to 10 power c n power b, this corresponds to only corresponds to the case with when I have the mean stress is 0. So I have tension, compression, everything we learned. So I take the mean stress is equal to 0. So what if the mean stress is not equal to 0? So everything that we learned, as I said, is when the mean stress is equal to 0. What if I have the applied stress is not, the mean stress here is not equal to 0? How do I find the stress amplitude that I need to use? I use this formula. So sigma A is over sigma equivalent plus sigma m over sigma ts is equal to 1. So sigma A is what? Is the stress amplitude. Sigma m is the mean stress, which is not equal to 0. And sigma s ts is the tensile stress. Sigma equivalent is the equivalent stress that I need to calculate. What is the sigma equivalent? So if I want to use sigma is equal to 10 power c and power b, normally I use the stress amplitude. But this is only valid if sigma m is equal to 0. If sigma m is not equal to 0, I need to find what we call an equivalent stress before calculating the formula, before using the formula. So let's take directly an example here to understand. So this directly we can understand the idea. So I have a cyclic stress, maximum value of 110 megapascal, the minimum value is 10 megapascal. The component is made of steel. We have all the values. You have all these properties of steel. We need to find the life of the component. What do you mean by life of the component? Life of the component means the number of cycles. So how many cycles it can live. That's what means the life of the component. If I have this alternating stress, 110 is maximum and 10 is minimum. The first thing to do, this is this alternating stress. The first thing to do is to calculate the mean stress. How do you calculate the mean stress? The mean stress is calculated as sigma mx plus sigma min over 2. So 110 plus 10 over 2, 60 megapascals, which means that the mean stress is not equal to 0. What does it mean the mean stress is not equal to 0? That I cannot use directly sigma is equal to 10 power c and power b. So we calculate the stress amplitude. The stress amplitude is sigma max minus sigma min over 2. So it's equal to 50 megapascal. I calculate the equivalent stress using this formula. So 50 over sigma equivalent plus 60, the mean stress over sigma ts equal to 1. I find the equivalent stress. And now this one I can use, for this one I can use 10 power c and power b. With b equal to 1 over 3 log sigma 1000 over sigma 10 power 6. Now the log here is log of 10. So it's the log of 10, is not the log of exponential. And I can calculate C, and finally I can find the number of cycles, because if I have sigma equivalent, I have C and I have V, the unknown here is N. So I can find N. So the idea that every time I have alternating stress, the first point is to calculate the mean stress. If it's not equal to 0, I need to find the equivalent stress using this formula with the amplitude, with the mean stress and the TS. And after that, I can do the classical method to relate the stress amplitude to the number of cycles. Finally, the final part about this. So this is what we need to understand. This problem here is everything we need to understand about the fatigue or the SN curve. We need to understand the meaning of sigma m, sigma. What do you mean by sigma? What's the relation between sigma and n? And that's summarize everything that we need to learn. That's another part here, that the fatigue limit that we set this fatigue limit, the stress under which even if I do it 100 infinity times it will not break. It has some depends also on some other factors, so it can change depending on the factor about the load, because what we did is about a tensile load only, about the surface finish, the size, and other factors. depending on the temperature and so it's not very important for us. For us, it will be given directly the sigma fs or the sigma prime. But just to understand, so according to the load, if I have an axial load, will be different than I have a bending load or a torsional load. For the size also, the specimen is less than 8 millimeters. It will be different. That is between is greater than 8 millimeters. So we need to multiply by a factor in order to find the fatigue limit. And we have some graphs here to show us the difference between different types of finishing, of surface finish. So if I have corroded or surface let's say between mirror polished here or corroded or machined, so this also have different surface factors. As I said, just need to understand that we have the modifying factors. This is an example here. This is an example that would summarize everything. A round bar undergoes a cyclic stress in bending with a maximum value of 500 megapascal and a minimum value of 100 minus 320 megapascal. With the component is made of steel, we have the tensile strength, the fatigue limit, and the sigma 1000. So the fatigue limit is given here for a fully reversed axial load. So without including any modifying factor of the ones that I just stated. Have the diameter of the bar, and the surface finish is considered as a common polish. What is the expected life? So the first thing to do always to calculate the stress amplitude and the So the first thing to do is to calculate the mean stress. Because it's different than zero, we need to find the equivalent stress. So we calculate the amplitude, and now we find the equivalent stress. I have now all these values. Now before I use this formula, the 10 power c times n power b, we need to find the modified fracture, the modified fatigue limit. So we need to multiply by a load factor, a surface factor, and a size factor. Then we apply and then we find n. So this example is just to show that we need to multiply by load, surface, and size. But for us, as I said, we directly will be given the fatigue limit. We don't need to now to study all of this or to memorize all of this. So for now, just let's take the basic equation, this equation and this equation. So here comes the end of this lecture and the end of this course of this semester. Now this chapter or this lecture is a bit long and a lot of ideas. We'll have the opportunity in the next semester in the strength of materials course to work also on similar topics. And I remind you also that this course and the next course of next year are basically the same course. So everything we learned this year, we should not forget it. We should keep it with us for next year. So in the tutorial, I have a lot of I will give you a lot of problems with detailed solutions about everything. So everything that you did not understand during the lecture, hopefully you will be able to understand during the tutorials. Thank you.